So welcome back to our usual auditorium. And today we have the pleasure of having Guilherme Ost from the nearby Federal University of Rio de Janeiro as our speaker. And he'll be talking about something related to random graphs and dynamics and neurons, I guess.
Yeah. So thank you very much, Roberto, for the invitation. I also would like to thank all the organizers for this very nice 5 weeks event. The program has been great, and then at least I have enjoyed a lot. So what I want to share here today with you is a part of an ongoing research project that has been done together with Eva Lecherbat from Paris 1 and Julien Chevalier from also in France in Grenoble. And instead of trying to give a general motivation for that, I've tried to jump directly to the model definition and then to state the questions that we are going to discuss here today. And after that, I try to motivate a little bit, okay? So what is the model? So the first ingredient for us is going to be what I'm denoting here by theta, which is simply a directed Erdős-Rényi random graph with n vertices and edge probability p, okay? So for me here, theta ij equals 1 indicates that there exists a directed edge from j to I, okay? Okay, so this is we understand quite well this model, and then what we do additionally is for each vertex, I assign a color which is either red or blue. For the time being, we can think of, I'm doing this deterministically, there will be a constraint in a minute, but for the moment, I mean, no matter how you do that, there are two colors, and I'm going to denote the set P plus, the set of red vertices, and P minus, the set of blue vertices, okay? And of course, these two sets, they form a partition of the vertex set 1n, okay? So just have an idea. So if you want to have just an illustration of this object, theta is going to be something like this, right? Vertices which are either red and blue, and they are connected by directed links, okay? So that's the first ingredient. And then what we do additionally is that for each vertex, we assign a sequence of binary random variables that, so if I'm looking at vertex I, this sequence will be denoted by xit. T is think of time index is indexed by the integer numbers, okay? And so if I look at time t, and I want just to keep track of all the configurations of the random variables xit for over the vertices, I'm going to use this notation xt, okay? And what we assume, and so this is the second ingredient of our model, is that conditionally on this random graph theta, this sequence of random vectors xt evolve as a stationary Markov chain on the Haber cube 0, 1 to the power n, okay, with the transitions which are given here, okay? So instead of trying to understand this, let me explain very briefly what it tells us. So it tells that if a given time, let's say t minus 1, I observe a sequence of zeros and ones, which is x, each vertex at the next time decides to, let's say, assign value 1 with probability p theta I of x, and value 0 with probability 1 minus p theta I of x, okay? So if you want, we can think of 1 as like some signal that is sent by the vertex at a given time, and 0, it means that that specific vertex decided to remain silent, okay? And for us, so we consider a very simple form for this transition probability, p theta I of x, which has this form here. So there is a parameter mu, which we can think of as a baseline parameter. And then what we do here, so I fix vertex I, so to compute the probability of sending a signal at the next time unit, what it does is it computes an average over all the neighbors that are in P plus, okay? I compute the average of ones, of signals sent in the previous time unit by all the neighbors which are in P+, so this is the first term, sorry. And then here, the second term, I do an average over the vertices, neighbors of I, so because theta I just count it if it's 1, over the set of P minus, and instead of computing the number of ones, I compute the number of zeros. Okay? So the idea is that for us, here P+, the vertices that are in P+, they act as, they excite the others, and the P minus, they inhibit the others. Okay? So that's the meaning of these two sets. And the parameters, the conditions here on mu and lambda is just to ensure that this thing here is always between 0 and 1. Okay? Is this clear for the moment? Okay, so that's the model. And the questions that I want to discuss here with you today are the following. So imagine that I give you a sample, x1, xt. The first question is, can I, for example, estimate the density of connections of the underlying random graph? So this is question 1. And question 2 is, what I can say, can I recover the set of excitatory vertices and the set of inhibitory vertices? Okay, so this is the 2 questions that I want to discuss with you. And let me mention that we're going to discuss this under two extra assumptions. So I won't assume that I know mu nor lambda, so this is an unknown. Instead, but I assume that the fraction of excitatory vertices and inhibitory vertices is known, it's close to 1/2. So the network somehow is balanced, if you want. Okay? So that's the condition that I need for the sets P+ and P-. Okay? So let me mention that we are particularly motivated by the statistical analysis of spiking networks of spiking neurons. And somehow the model that we are considering here can be seen as a simplification, for example, of point processes that are called Hawkes processes in the literature. So we are considering a discretization of such models. And let me just go back here. So you could imagine that instead of, where is the point? You could imagine that instead of considering keep track of just one time unit in the past, I could generalize this to consider more and more time units in the past. And then by doing that, I would have a sum here over different time units. And if I do that, I would be very close to the discrete time version of these Hawkes processes, okay? And of course, Hawkes processes, well, anyway, you tell me if it's not, it's too complicated, too unclear. Okay? So is the model sufficiently clear? Okay, so let me try to discuss with you the first question, okay? So, the idea that we wanted just to find a very simple algorithm or estimator to the parameter P. And to do that, somehow we have at least, well, we have 3 unknown parameters, that is mu, lambda, and P. So it's kind of natural to try to estimate each of these parameters, make some function of this to estimate P. So that's why, that's what we do. So to explain the estimators, let me just introduce some notation. So ZIT here for me is just, so I'm fixing vertex I, I'm counting how many signals or how many ones I see from time 1 to t, okay? So it would correspond here in this image, if t is here, it would correspond just the number of ones in this blue rectangle, okay? And another important notation for us is this z bar t. So zt would correspond the vector of zit, varying I, and z bar t is just the empirical average of this vector, okay? So this is, if you want to have in a picture, is if t is here, I take this square, I sum all the ones, and then divide by the number of rows of this matrix, okay? So that's what is the meaning of this bar t. Okay, so the first guy, the first estimator, is the simplest thing you can imagine. Is just what we call this spatial temporal mean. So I take my time window capital T, and I compute for each coordinate how many, let's say, signals each vertex has emitted from time 1 to capital T, and I do the empirical average, and it's still divided by T. Okay, so that's the first thing. And the other two one is the temporal variance, which is something very strange. Well, not very strange, but I mean, I'm not a statistician, so what I know how to do is mean and variance. So this is something that is temporal variance, and the second guy is what we call spatial variance. And then I just want to give you some ideas of how we ended up with such two estimators, okay? So I do this in the blackboard. So for the temporal variance, so imagine that here is my time window T. So here I have each line here corresponds to the activity of a given vertex, okay? And what I do here is just, first of all, I do some binning of this interval 1t when the bin size is some quantity called delta. So I have delta, 2 delta, and so on. Okay? And imagine that this is, I don't know, it's t over delta times delta. Okay? Assume that t is, I can divide t by delta. Okay? So what I do here, I can compute, for example, the average number of signals I observe in this part of the data, okay? And this is exactly, in the notation that we use, this is exactly this z bar t delta minus z bar t minus 1 delta, okay? And then what we do, so for each bin, I have this random variable, I can compute its variance, okay? And so this is more or less, so I can compute its empirical variance, and this quantity W delta that you see here on the screen is essentially, is equal to n divided by delta times this empirical variance. Okay? And then you arrive at this quantity W of delta, and we can show, it turns out that we can show that this converges to some quantity, okay? And then what we do is, okay, we do the same, we consider the same quantity, the same random variable, but the scale that we consider here is twice as large. So it's 2 delta, okay? And we can show that this thing converges to the same quantity, okay? But then it turns out that when I consider that, so that's why I have, so this quantity converges to the same quantity W, this also, and then I multiply by 2 to have something, the same limit, right? But by studying their difference, by considering the difference, the convergence is much faster, okay, than by considering just each one individually. So that's why we ended up with this thing here, okay? Okay, so that's the main idea for this temporal variance. And for the spatial variance, we just use this fact that, for example, we start from this equation, var of z1t. So suppose I want to compute the variance of, I take vertex 1, I compute how many signals it sends from 1 to t, I compute the variance of this thing, okay? And I can do this by using this, I think in English it's this EVA formula, I don't know, EVA formula, which is the expectation of the variance conditionally on the environment plus the var of the conditional expectation of Z1t. Okay? And then, so this guy we know how to estimate. I mean, there is something that maybe is not so clear because here the environment is not fixed, right? So what you do to estimate this, you would generate several random environments and look to this quantity here, right? But instead of this, we have just one, but it turns out that since there is some symmetry in the model, I can estimate this by looking into the same environment, but instead of looking to the vertex 1, I look to the vertex 1, 2, 3, etc. So I can estimate by this. Okay. And so this we know how to estimate, and we also know how to estimate this quantity here. So let me try to explain a little bit. So for example, if I start from this formula here, var of Z1t, so this is, by our definitions, just the var of the sum, right? Of the axis. So I use, the var of the sum is the sum of the variance plus the covariance, right? So this is, here's t, sorry. And here is the isomer for S and T that are different, the conditional covariance. Okay. And so by stationarity, so remember that conditional theta, we assume that we have something which is stationary. So this is the same as t times the variance, let's say, of xi. So it's here is 1, sorry. It's 1, here's also, I apologize, and here's S. And so this is not very clear, but I mean, you remember that in the definition of the transition probability, the effect that a given vertex has in any other vertex, there is a factor 1 over n in front. So it's not very surprising that the absolute value of this is at most a constant divided by n, okay? So this we show. And of course, the covariance depends on the distance between the time indices here. And this is scaled by this factor 1 over lambda. Okay? Right? And so somehow, if I sum over S and T here, so this will be something summable when I send n to infinity, so this is, this is very small, right? So even if there is some dependence, in this variance here, it looks like something which is independent. It's T times this variance, okay? So that's I'm almost there, just. So the plus something small, right? And then, so this something is a Bernoulli random variable, so this is nothing more than the expectation, right? One minus the expectation. Right? And and this is, we know how to estimate. This is just the number of signals that you observe by the vertex I between 1 and t and divide by t, right? And so if you take more or less, if you take this quantity here, subtract the estimation for this, and still you need to, you have to find the correct scale, which means that I have to multiply by n divided by t squared. You get exactly the v hat here, okay? That's more or less the idea. Okay. So if you consider these three estimators, what we can show is the following. So we can find so the first one I call it m hat. The v hat, let me go back here. The v hat is the spatial variance, and the w hat is the temporal variance. So with this notation, we can prove the following. We can prove that we can find m, v, and w, their limits, and we can show for each one of them that they converge in probability, and also we can quantify the rate in which this convergence takes place. Okay? And, and perhaps here the important thing here is that, for example, in order that v hat converges to its limit, I need a condition between the n and t. So here there is square root of n divided by t. So there is a relation between the size of the network and the time window that the observation time. Okay? And it turns out that each limit m, v, and w, they are given by this expression here. Of course, they should depend and then depend on the other parameters mu, lambda, and p, etc. in a complicated way, right? More or less. So because of the time, I want to explain how I can somehow heuristically, in the paper we try to give some ideas of how we ended up with each one of these expressions, and I just want to explain for the mean how to arrive at this expression because it's much easier, okay? Okay, so heuristics, let's say. For limit for m hat, let's say. Okay. So I didn't ask, but can you read what I write here? Okay. So the estimator, recall, is this m hat is just 1 over t of this sum over 1 over n of this z I t over n. So let me write it this way. Okay? So if I apply a sort of law of large numbers, because you remember this is a sum, right? If I apply a sort of ergodic theorem here, I know that this is going to converge to well, let me write it one more time here, more specifically. So if I apply a sort of ergodic theorem here, so this is going to converge to the average over the space of one of these variables, right? So this is going to converge to some value, which I'm calling here mi of n, which is just, so the environment is fixed, right? I'm always thinking that the environment is fixed, of the expectation of xi1, because I'm assuming that the model is under the invariant distribution already. Okay, so I know this. So if I plug this fact here, I expect that this is close to 1 over n plus, and here I have this min. Okay. And so it's not true that for a fixed environment, any of the vertices have the same, they are the same. But if you think a little bit and you imagine that the size of the network is very large, this is more or less true. Okay? So in fact, each mi of n, they are essentially the same, and I'm going to call them, so this is equals to all of them, so this is M1 of n, okay? So if this is the case, this thing here, this empirical average over the mi's is equals to M1 of n, okay? And then we can get an equation for this very easily. So our limit is the limit of this thing. And let me try to explain and give you an equation for this. So by definition, this is just the expectation, the probability of observing. I take vertex 1. I'm looking at time 1. I ask you what is the expected value of x11. Okay. So I can use the Markov property, right? So again, sorry, this is fixed. I can conditionally take the conditional expectation with respect to time 0, right? And then, so this is going to give me what I defined at the beginning, this p theta 1 of x0, right? The probability of observing a signal in vertex 1 given the past configuration. And we have a formula for this, no? So this is mu plus 1 minus lambda divided by n, sum over the j's which are in the excitatory set, theta ij, 1 minus xj0 plus the guys which are in the inhibitory, theta ij, 1 minus, well, this is the formula, right? And then I just use the linearity of the expectation, so this is mu plus 1 minus lambda over n. So since somehow I'm taking the expectation conditionally on theta, so this expectation comes here, so this is, it's constant, right? And the expectation of this guy is mj of n, sub n, right? So the expectation, right? Oh, let me write it here. Okay? And so by our definition, this is exactly what? That should be mj of n, but they are all equal to m1 of n, right? So this is m1 of n. And here's the same thing. Right? So what I have here, it's now I can put as a factor here in front of all of this. So I do it here. So if I combine all these together, I get this m1 of n equals to mu plus 1 over lambda times m1 of n. And then you agree with me that I have a sum over theta ij, sum over j, divided by n, and something here which this sum here over the sum of theta ij over g minus, and something similar here with m1 in front. Right, so let me just copy this. So let me write it this way. okay? So now I think we all agree that in fact, so this is going to converge by the law of large numbers to p over 2. So this is going to converge to the same thing, p over 2. So this is 0. And then it remains just mu plus 1 minus lambda times p over 2 here. And that's exactly the expression for m. Okay? So that's to give an idea, but we could do something for the v and w, but it's more complicated. Okay? Good. Okay, let me see. Yeah. Good. And just a quick comment here. I mean, as the user, let's say if the user, I mean, if someone would like to use the temporal variance, we should tune the parameter delta over there. And we are kind of convinced that the delta, which is of order log of t, gives you the best, I mean, the fast rate of convergence. Okay? So that's what I would advise to use. And okay, so the message up to this point is the following. So we have three estimators. We find their limit. They are given by that expression, but I mean, remember our goal here is to estimate p, right? So the point is, magically, I would like to somehow be able to invert this system to get p, mu, and lambda. And it turns out that in this case, it's very easy. Okay, so I want to convince you this by doing the computations on the blackboard. Okay? So what I want to show is by knowing, so I'm assuming that I know m, v, and w, and I want to isolate p, mu, and lambda, right? So let's have a look at the third equation. So you agree that in the third equation, I can immediately see that if I take w, divide by m, 1 minus m, subtract 1, this gives us 1 minus lambda times p, right? Do you agree? So this means that I know how to estimate this value somehow, right? Then, if I look at the first equation, then what we see is that mu, so one of the parameters that you want to estimate, can be written as m minus, 1 minus lambda p over 2. So if I combine these two things together, this means that there exists a function, right, which depends on w and m, which gives me mu, right? So, yeah. So that's the first thing. But then, if now I look to the second equation, so second equation, gives me what? It gives me that v, if I divide by m squared minus m plus 1/2, this is equals to, let me write in this way, 1 minus lambda times 1 minus lambda times p, so that's something together, minus 1 minus lambda p squared. Do you agree with that? So this means, so this guy is a function of m and w, this guy as well. So somehow I'm trying to convince you that I know how to, I mean, there is a function which depends on v, m, and w, which gives me 1 minus lambda. Okay, so this implies is some function of m, v, and w, right? And if we arrive at this point, then I just come back here and then say, well, so this gives me p by the end of the day, right? Okay? So there is a formal way of doing all that. So that's the content, let's say, of the next slide, but I think you all agree with me, right? Yeah, so I'm showing that at least in this case, there exists some function phi that whenever I apply m, v, and w, satisfying the equation gives me mu, lambda, and p, okay? And then, so at least in principle, the conclusion that I get from everything that we have discussed so far is the following. If I take delta like log of t, and then I'm considering this asymptotic setting where t goes to infinity and when n goes to infinity, but in such a way that square root of n divided by t of n goes to t of n sub n goes to 0, then I can take the estimators m hat, v hat, w hat, apply to this non-function. So we know that, this function is sufficiently regular that the convergence of m hat, v hat, and w hat will imply the convergence of the phi to m, v, and w, and this in turn will give me the mu, lambda, and p, okay? So in particular, if I look at the third coordinate of this function phi, it gives me the p, okay? So that's more or less the idea. And of course, we can provide also, we know that this function is sufficiently regular that we can somehow transfer the rate of convergence of the mu hat, v hat, w hat to phi as well. In the paper we discussed, we show that with the same three estimators, it's possible to consider the case where the network is, the R plus here can be, so the R plus is the asymptotic fraction of excitatory vertices of my network, can be at least larger than 1/2, can be also very small, but it turns out that this is something that is kind of, we understand why it should be this way at the first place, but there are some values that the corresponding system that I show you for the case R plus equals to 1/2 is not invertible. Okay, so we are kind of, we don't know how to do in these cases. So, okay, so somehow, if the fraction of excitatory vertices is at least 1/2, we are fine. If it's very small, fine, but there is this region here where we don't know how to do. Well, at least this method doesn't work. Okay? Okay, so that's what I wanted to say about this problem for estimating P. So in the remaining 15 minutes, I just want to discuss the question how to recover P plus and P minus, which is somehow is related to this community detection problem, okay? So here, the idea is, the important thing to remember here is when I look to this, let me write it in this way, right? So whenever I write here, so this thing here is what I was calling Pi of x, small x, right? And so this is mu. Let me give you the definition again. X, what is small x here? Okay. So if I want just to say, well, I take a vertex j, and I want to know if this vertex is either in p plus or p minus, I can somehow, I mean, this information is reading already here. Because somehow, I mean, I think you all agree with me, if j has a 1 here at the time t minus 1, this should increase the chances of observing a 1 for vertex I at time t, right? So this tells us that if I look to this one-time unit lag covariance, so I'm computing the covariance between xj at time 0 and with xi at time 1, so this should tell me, should at least help me to find this p plus and p minus, right? So let me define this quantity, and also this quantity Sij, which is just the environment, theta ij with a plus if j is in p plus, and with a minus in front if j is in p minus. Okay, just a signed version of the environment. Okay, so if you define these two quantities and the corresponding, and then I consider the corresponding matrices, what we can show is that if I scale this one time unit lagged covariance matrix by n, so this converges to this matrix S times some quantity here, which is, is the m1 minus n times 1 minus lambda. Okay, we can show that. So we can somehow find exactly the limits of n times this covariance matrix. Okay. And this norm here is just the maximum distance between all the entries of the matrices. Okay, so we can show that. And once we arrive here, what we do, if I look to this matrix here, Sij, if I fix column j and sum over I, right? The sign, so if I take j, let's say in p plus, this is going to be theta ij. If I sum over the rows, so this will be close to something related to p at least, right? And if I take a j and sum, which is in p minus, so there will be a sign, right? Minus sign in front. So this tells me that if I, as I just said, if I define this vector sigma j, which is for each column of this matrix sigma 1, I sum over the rows, and I just use the previous result, we can prove, in fact, that this vector sigma converges to the vector of 1s in p plus and minus in p minus times a constant. Okay? And so this constant here is this previous one times p. Okay? And again, the rate is the same, it's log of square root of log of n over n. And once I arrive here, I can, of course, if I approximate very well, if I approximate very well the sigma, so if sigma is very close to this vector, for example, this means that epsilon has to be smaller than this quantity here, I can recover the set p plus by looking to the signs of this vector. Okay? So in the slides, this is more complicated, but what I'm saying here is that there is some quantity here that whenever j is in p plus, the vector, sorry, let me write it here. This is 1 minus lambda m, 1 minus m. So if I look at this vector here, right, when I take a j in p plus, its value is this quantity here. If I take a j which is in p minus, it's minus this quantity, right? And if I approximate, if the sigma is very close to this vector uniformly, so it means that if I approximate very well, so let's say if this is epsilon, Then I look at the coordinate of sigma j with j in p plus. Its value is going to be here, right? And if I take a j which is in p minus, the coordinate of sigma j is going to be here. So if I look at the signs, I will distinguish between p plus and p minus. Okay? So that's what I'm saying here. We can quantify the probability of occurrence of this set. But of course, in practice, I cannot use sigma because I don't know this matrix sigma 1, right? Yes, say it again.
Where is the randomness here in this expression?
It's hidden in the environment.
Here you had sigma hat, and then it went to just sigma.
No. Sorry. Here you're saying.
Yes.
Yeah, because, I did it. Well, this is kind of, it's hidden, right? But in the definition of this sigma 1 ij, I'm conditionally on the environment. So this still depends on the environment, okay? So the randomness is hidden there. So when I write here this expectation, I'm taking the expectation with respect to the random environment. Okay? Right. Thanks for the question. Okay? So that's the message here. Then at this point, I cannot estimate, I cannot use sigma because I don't know the matrix, right? So instead of this, I can estimate the sigma by using the sample, right? So if I do that, the corresponding estimator will be something like this. I have a sum over I, and then I just estimate the covariance as usually you will do, right? And then we can quantify, and here I don't know if we are very, if probably they are better bounds than the ones we got here, but we can quantify the expectation between the subnorm between sigma and sigma hat and sigma, and it's like n over square root of t times this log factor, right? But then we can quantify this, and if I put everything together, basically, I use the fact that if sigma is sufficiently close to the vector of indicator of p plus, p minus, and at the same time, sigma hat is very close to sigma, I put these two things together. In principle, I can recover the set of excitatory vertices just by looking to the sign of sigma hat plus, j. And so that's the way we can find these two sets, right? I take the vector sigma hat, just looked at for each coordinate its sign. If it's positive, so this is going to be estimated as excitatory vertex, and otherwise is inhibitory. Okay, so this gives me a procedure to find the sets. Okay. And then, so because I'm kind of arriving, I'm taking too much time, more than expected. So here I'm going to be quick, very quick. But by combining the rates that the bounds that we got for the expectations, we arrive at a sufficient condition to ensure that we can actually exactly recover the sets. Okay, and here is like, if this epsilon goes to 0, sufficiently is low when n, and t goes to infinity sufficiently fast, such that this condition here holds, we can prove that the probability of exactly recover these two sets goes to 1. Okay? And morally, here we are imposing something stronger than estimating p, because for p it was square root of n divided by t, has to go to 0, and somehow here I have n divided by square root of t. Okay, so but at this point I'm not very convinced that these are very tight bounds. Okay, in any case. Okay, but somehow it's stronger in this sense. We require more to recover these sets than to estimate p. Okay, so just to conclude, I just want to point some open questions. The first question is, okay, we would like to have some lower bounds, so to have an idea if we can do better or not, right? Then we'd like to know if if you can generalize for more general forms than this, let's say, additive transition probability, right? We would like to know if I can put some linear function here in front to be closer to these GLM models, right? I don't know if it helps, so I think it's natural, but I don't know if it helps knowing P plus and P minus to estimate P, right? Because usually, if in advance someone gives me the set P plus and P minus, I could somehow use the form of the transition probability more directly to estimate P. So in principle, this gives me more information, but we don't know if you can really make use of this. Okay. And then, of course, the fourth question is if I can consider, what I can say for more general random graph models like stochastic block models or these RDPG as well. Okay. So that's it. I stop here. Thank you very much for the attention.
I have a couple of questions. So, in principle, suppose you don't care as much about estimating P, you just want to estimate the communities, right? The excitatory and inhibitory. So you could take sparsor graphs too, right? In principle, if you normalize correctly, and of course, you kind of might lose P in the normalization somehow, right?
Mm-hmm.
So,
mm-hmm.
okay, that's question number one, and you seem to agree with me.
Mm-hmm.
Question number two, I would think, and maybe that's not entirely obvious, but if you have something like an exponential of the sum, right, kind of GLM kind of thing,
Mm-hmm.
it would seem that it should be able to, you have these three equations, right, for the quantities you want to estimate, right?
Yeah.
It should be it should be possible to guess what the right equation should be like in a more general model, right? So.
For the mean, of course.
Yes.
For the other two, I guess so, but I'm not completely sure. But I guess it should be possible. It should be possible.
Right.
Yeah, it should be possible.
Yeah, I'm not sure if it's an easy thing to prove, but that actually works in the same way that this works, but it should be possible to at least guess what the right thing should be.
Yeah, I just want to mention that, for example, at this moment, there are, with two master's students and other two colleagues in the UFRJ, we are kind of considering the model here where here we introduced somehow the SPM structure, saying that if I take a vertex I, which is in P plus, so this will be parameter P, let's say, I don't know, and here would be Q. And then if you try, if you ask the same question, can I recover P plus and P minus? And it's very, for me, it's very surprising that if they have different sizes, I can discriminate between these two sets just by looking to the average. It's very simple to show that. So would correspond, just look to the corresponding M here, M hat somehow. But then if they have equally, if the nectar is balanced, then I'm kind of obliged to look to the covariance, for example. And then I can distinguish between these two. And so I think, even though the model is very simple somehow, I think there are several questions that are very interesting to investigate in models like this, which is related to more standard questions like models like SPM, etc.
So here you looked at the exact recovery. If you only want to know like a non-trivial fraction.
Yeah, we didn't investigate this question, but certainly it's very interesting. And but yeah, we didn't investigate. We didn't investigate yet. And just to try to answer the questions of Roberto's questions about the case where the graph is sparse, of course we can say, well, imagine that at the beginning my p scales with n like is a constant divided by n. And then maybe I could just reconsider a different renormalization here and try to ask if I still could estimate not p, but maybe the degree, I mean, how many neighbors I have, because I have just a few of them. Then perhaps just looking at the covariance structure, this would give me the answer for that. So that would be my guess, but no proof at the moment. So I guess it's possible, but not clear.
Can you say something more about where this problem comes from?
Oh yeah, no, that's a very, very good question. So, so we got very inspired by one paper from, their names is Delattre and Fournier. They have formulated, let's say, the same problem. I should have said that earlier. But then they were considered these Hawkes processes. So they have this, I mean, you have point processes on R plus, let's say, and you have the intensity, lambda t, that for them, well, let's say in my notation will be this mu plus 1 over n plus something like this. I guess they have some function here, t minus s. So we have your point processes z, and then the intensity in their case, so this is a function which depends on the past events, the past jumps, that are codified here. And in their case, they consider exactly this form. So we are somehow, each time you observe a jump for the point process j, it increases the intensity for I, let me put it here, by a quantity age of which that, I mean, it jumps at time j, and then what it gives to vertex I at time t depends on the difference, and this is a function of age of the difference. And then they have this something very similar here to the graph, right? But then in their case there is no inhibition; it's just excitation. Apart from the model, also their techniques are completely different from ours. So yeah, but we somehow got inspired by this paper. So it's Fournier. If you want to Google it, it's Fournier and Delattre. I don't know if it's 2L or not, or 2T. So I guess it's Electronic Journal of Statistics, 2016, something like this. Okay. Yeah, and also, I mean, just to maybe to conclude, because it's interesting, because they were saying, and the same phenomena takes place here, that at the first place, this problem of estimating p doesn't seem to be well posed. Because, I mean, if you look at the dynamics of a given vertex, when the size of the network is very large, then it looks like, in our case, like a Bernoulli process with parameter m, which is this mu plus 1 minus lambda p over 2. So at the beginning, when you look, I mean, what you would do, like, well, I looked at the dynamics of a given vertex when the size is very large. So this is just a Bernoulli, a sequence of Bernoulli random variables with a given parameter m. And if you look only this, you cannot identify p, for example. It's not identified because there's this product between 1 minus lambda and p, right? And then you could say, well, what happens if I look k of them? So it turns out by this propagation of chaos property, they all be independent as well with this, I mean, Bernoulli process with the same parameter. You wouldn't be able to find p in this case again. And then somehow what you really need to do is a function of everything to to try to solve the problem. So in their case, that was the main motivation, I would say. And whereas here, so we have also this community structure that they don't consider, et cetera, et cetera.
Any more questions? Well, if not, let's thank Guilherme again.